This lecture is about the latent Dirichlet allocation, or LDA. In this lecture, we're going to continue talking about topic models. In particular, we're going to talk about some extension of PLSA, and one of them is LDA, or latent Dirichlet allocation. So the plan for this lecture is to cover two things. One is to extend the PLSA with prior knowledge. That would allow us to have, in some sense, a user-controlled PLSA. So it doesn't blindly just listen to data, but also would listen to our needs. The second is to extend the PLSA as a generative model, a fully generative model. This has led to the development of latent Dirichlet allocation, or LDA. So first, let's talk about the PLSA with prior knowledge. Now, in practice, when we apply PLSA to analyze text data, we might have additional knowledge that we want to inject to guide the analysis. The standard PLSA is going to blindly listen to the data by using maximum likelihood estimate. We're going to just fit the data as much as we can and get some insight about data. This is also very useful, but sometimes a user might have some expectations about which topics to analyze. For example, we might expect to see retrieval models as a topic in information retrieval. We also may be interested in certain aspects such as battery and memory when looking at the opinions about a laptop, because the user is particularly interested in these aspects. Now, a user may also have knowledge about the topic coverage, and we may know which topic is definitely not covered in which document or is covered in the document. For example, we might have seen those tags, topical tags assigned to the documents, and those tags could be treated as topics. If we do that, then a document can only be generated using topics corresponding to the tags already assigned to the document. If a document is not assigned a tag, we're going to say there's no way for using that topic to generate the document. The document must be generated by using the topics corresponding to the assigned tags. So the question is, how can we incorporate such knowledge into PLSA? It turns out that there's a very elegant way of doing that, and that's to incorporate such knowledge as priors on the models. And you may recall in Bayesian inference, we use prior together with data to estimate parameters, and this is precisely what will happen. So in this case, we can use maximum a posteriori estimate, also called map estimate. And the formula is given here. Basically, it's to maximize the posterior distribution probability. And this is a combination of the likelihood of data and the prior. So what would happen is that we're going to have an estimate that listens to the data and also listens to our prior preferences. We can use this prior, which is denoted as P of lambda, to encode all kinds of preferences and constraints. So for example, we can use this to encode the need of having precisely one background topic. Now, this can be encoded as a prior, because we can say the prior for the parameters is only non-zero if the parameters contain one topic that's equivalent to the background language model. In other words, in other cases, if it's not like that, we're going to say the prior says it's impossible. So the probability of that kind of model setting would be zero according to our prior. So now we can also, for example, use the prior to force particular choice of topic to have a probability of a certain number. For example, we can force the document D to choose topic 1 with probability of 1/2. Or we can prevent a topic from being used in generated document. So we can say the third topic should not be used to generate the document D, and we set the pi value to 0 for that topic. We can also use the prior to favor a set of parameters with topics that assign high probabilities to some particular words. In this case, we're not going to say it's impossible, but we're going to just strongly favor certain kind of distributions. And you'll see example later. The map can be computed using a similar EM algorithm as we have used for the maximum likelihood estimate. with just some modification to smooth the parameters to reflect the prior preferences. And in such an estimator, if we use a special form of the prior called a conjugate prior, then the functional form of the prior will be similar to the data. As a result, we can combine the two, and the consequence is that you can basically convert the inference of the prior into the inference of having additional pseudo data, because the two functional forms are the same and they can be combined, so the effect is as if we had more data. And this is convenient for computation. It doesn't mean conjugate prior is the best way to define prior. So now let's look at a specific example. Suppose the user is particularly interested in battery life of a laptop, and we're analyzing reviews. So the prior says that the distribution should contain one distribution that would assign high probabilities to battery and life. So we're going to say, well, there's a distribution that's entirely concentrated on battery life, and our prior says that one of your distributions should be very similar to this. Now, if we use map estimate with the conjugate prior, which is Dirichlet prior, Dirichlet distribution based on this preference, then the only difference in the EM algorithm is in the M step. When we re-estimate word distributions, we are going to add additional counts to reflect our prior. Right? So here you can see the pseudo counts are defined based on the probability of words in our prior. So battery, obviously, will have a high pseudo count. Similarly, life would have also high pseudo counts. All the other words will have zero pseudo counts because their probability is zero in the prior. And you see, this is also controlled by a parameter mu, and we're going to add mu multiplied by the probability of W given our prior distribution to the collected counts when we re-estimate this word distribution. Right, so this is the only step that's changed, and the change happened here. And before, we just collected the counts of words that we believe have been generated from this topic. But now we force this distribution to give more probabilities to these words by adding them to the pseudo counts. So to artificially, in fact, we artificially inflate their probabilities. And to make this a distribution, we also need to add this many pseudo counts to the denominator. This is the total sum of all the pseudo counts we have added for all the words. This would make this again a distribution. Now, this is intuitively very reasonable way of modifying EM algorithm. And theoretically speaking, this still works, and it computes the map estimator. It's useful to think about two specific extreme cases of mu. Now, looking at the picture, think about what would happen if we set mu to 0. Well, that's essentially to remove this prior. So mu, in some sense, indicates our strength on prior. Now, what would happen if we set mu to positive infinity? Well, that's to say this prior is so strong that we're not going to listen to the data at all. So in the end, you can see, in this case, we're going to make one distribution fixed to the prior. You see why? When mu is infinity, we basically let this one dominate. In fact, we're going to set this one to precise this distribution. So in this case, it is this distribution. And that's why we said the background language model is in fact a way to impose a prior, because we force one distribution to be exactly the same as what we give. That's the background distribution. So in this case, we can even force the distribution to entirely focus on battery life. But of course, this won't work well because it cannot attract other words. It would affect the accuracy of counting topics about the battery life. So in practice, mu is set somewhere in between, of course. So this is one way to impose a prior. We can also impose some other constraints. For example, we can set any parameters to a constant, including 0 as needed. For example, we may want to set one of the pi's to 0. And this would mean we don't allow that topic to participate in generating that document. And this is only reasonable, of course, when we have prior knowledge that strongly suggests this.